So hi everyone. So my name is Eliška, and I'm gonna talk about this thing I do in my research, which is called quantum machine learning methods for malware detection, or just quantum machine learning for malware detection. Like this, it sounds like a bunch of buzzwords put together. I'm gonna, during this presentation, hopefully explain all of them. I assume, I don't know much about this meeting, but I assume that you have like some knowledge about machine learning. So I'm not gonna explain machine learning in depth much. And I assume you don't know maybe a lot about quantum. I don't know. Maybe is there anyone who knows anything about quantum computers or does anything in the field? No, good. Because otherwise it would ruin like half of my presentation. So good. So starting with, before we were gonna talk about the quantum machine learning, start with what is quantum computer. So what is it? I would say it's just like a different type of computer. Wow, groundbreaking, I know, but bear with me. Maybe a different question to start with is, what is a classical computer? I guess like all of us kind of know, but how would you explain it? Like this is a computer, this is a computer. But from an information theory perspective, we can look at it just like some machine for processing information. What does it mean? The simplest unit of information when looking at it from the information theory perspective is bit. Bit can have two values, 0 and 1, and it's what our classical computers work with. And when you put lots of these bits together, they form a system. The system is called a computer. These bits have these values, some specific lots of bit values put together. They form some state of the system, so some state of the computer. And what can you do with all these bits? You can apply some logical operations to them. These are called logical gates. And you can somehow modify the information. And that's basically what classical computers do from the theory perspective. The important thing to highlight about this that these computation operations are predictable and deterministic. What does it mean? When I take two bits and I apply whatever computation thing on them, whatever logical gate, I can 100% say what the outcome be. If I put AND on two bits, I know what the outcome would be based on the values. And why am I explaining this? It's actually like the main difference, what makes quantum computer a different type of computer. Because it is also a machine for processing information, and it also works with some units of information. The difference is in quantum computing, we don't call them bits. For example, in what you may heard of, we call them qubits, but qubits are not the only type of unit of information we work with in quantum computing, but they are the most famous ones. So for the purpose of this talk, I'm gonna talk about qubits, but they're not just qubits, but qubits are also some kind of unit of information. When you put many of these qubits together, they also form a system, and the system is not a classical computer.
Sorry, we have some issue with the slides. I'm gonna change how we share. All right, I'm really sorry about this, but it should be working now. Yeah, thanks, thank you.
So maybe we can check before I'm gonna talk again.
Yes,
so is it really
working.
sharing?
Yes, it is. I can see it here.
Okay,
Thank
nice.
You.
So this was a quick break, but actually it's a nice use case for what I'm gonna talk later. So nice, you can see that even classical computers can fail sometimes, you know. In these cases, I usually like to say that like I don't understand computers, so I can't help. You know, this is not a quantum computer, the classical one. What is it? But with the quantum computer, so coming back to this analogy, so quantum computer also is a machine for processing information, and also works with some units of information. They are not bits, but like different types of units. We're gonna call them qubits. When you put many qubits together, they're gonna form a system, and the system is, in this case, quantum computer. And when you have certain values for these qubits, they form some state. And in terms of quantum computing, we're gonna call it quantum state. The same way as you can apply logical gates in classical computers, you can do something similar in quantum computers. When you apply these quantum gates, again, everything here is quantum. So when you apply these quantum gates, you are also somehow changing or modifying the information, and the information flows through the computer the same way as in the classical one. So what is the difference then, apart from having a different logical gates? Is that whereas in classical computer, the outcome of this operation is 100% predictable, in quantum computers, it is based on probability. So when you apply some quantum gate to some quantum state, you cannot say for 100% this will be the outcome. You can only say it with certain probability. And this is very important because you can somehow like interfere with these probabilities, and you can modify the flow of the information so it ends up in a situation you would like to see with high probability or with lower probability. And you find out the result when you measure it. There are like so many underlying physical concepts, stuff about quantum computers I could talk about, but like this is the main thing to take from it, that it's just like a different way how the information flows. And in very general way, you can just think of it as just a different type of computer. The same way as you can use your phone on your laptop and you don't have to know the physical or architecture details about that device. You don't have to know it about the quantum computer to understand the stuff I'm going to talk about later, hopefully. Then, why are quantum computers interesting? You may probably heard about like some of these statements in the news. Are just a bunch of screenshots I found out when I just like opened the news page on like Google. When you put quantum computing, what you're gonna find out. Usually, because I come from security background, usually I guess that the most common thing people ask me in my field about quantum computers is, will they break RSA, and when? Does it pose some security threat on the cryptography and stuff like that? I would say yes, but we are not there yet. For all these types of things, we would need a computer, which is called universally fault-tolerant computer. That means a very advanced hardware device, which is, as it says, tolerant, like fault-tolerant. What does it mean? One more important thing about quantum computers, the only physical part which I think it's important to know about. Quantum computers are very sensitive to the interaction with environment in terms of how it affects the information which is stored in them. When I leave my phone left on this table, it won't change the content in the phone. In terms of like, I don't know, if you would write me a message, it will still stay there. If this would be a quantum phone, it would heavily interact with the environment. And if I wouldn't have enough qubits, these operations units, to correct the errors which comes up from this interaction with environment, it would lead to some errors, and it would somehow like destroy the information I have in the phone. And to preserve this information in this quantum device, we need a lot of these qubits to be able to correct these mistakes. It's a similar way as in classical cryptography. You have error correcting codes. When you process information, for example, when you take like some normal signal and you receive some signal, and the signal you receive, maybe your detector is not 100% perfect. So you receive the signal with some mistakes. For example, you are missing every third bit or something like that. You can apply some error connection code, which will still help you to like get the information you need from the signal, even though you don't have all the bits, all the information about the information you're getting. And this is something similar. Even though you lose some information due to the interaction with environment, you can still correct it. But we don't have these super fancy quantum computers which can do this on a large scale to be able to implement these types of algorithms, which are mentioned here. Most of these algorithms, they rely on these universally fault-tolerant quantum computers, and they have some theoretically proven advantage, but I don't think like we're gonna have these quantum computers anytime soon. If I would be from IBM or something like this, at this point, I would present you some roadmap with like some predictions when we're gonna get these universally fault-tolerant quantum computers. But at this point, it's all just like guessing. And I think we're gonna have them in like next, I don't know, 10, 20 years. That doesn't mean it's like, it still makes sense to like think about post-quantum cryptography and stuff like that, but yeah, not the point of this presentation. But we have some quantum computers already. They are just like not like this. They can do stuff, but they are called NISQ devices. That stands for Noisy Intermediate Scale Quantum Devices. What does it mean? Noisy stands for this interaction with environment. They are not perfectly like, I don't know, in like some box which cannot interact with the environment. They interact, therefore they get these errors, so they are noisy. Intermediate scale means that they don't have enough qubits to correct this noise from the environment. They have a lot of qubits, but not enough, and they can do stuff. The question is what? And this is how does it look like on some, like, this is how these devices looks like on some PR photos, like just like some fancy gold thing. This is how it usually looks to me. It's just like some box in some web UI from where I see like which hardware backends I have available, what are the properties of these certain types of backends I can access, and I can choose from them. Why am I adding this here is that one of the common questions, surprisingly, I get is if I ever seen a quantum computer in real life. The question is, the answer is yes, not exactly this one, but yes. But another analogy to real life, especially if you come from machine learning background, the same way as you don't have to see your cloud servers on which you run your computations, you don't have to see your quantum computers to run computations on them. So just an analogy to that. So much talking and not yet mention of quantum machine learning. Why quantum machine learning currently is one of the most, or not like most, but very active research area on this NISQ hardware. Because we have these quantum computers, which are these NISQ devices, and sorry. And the question is what we can do with them. And one of the research area is, can we do something called quantum machine learning? What does it mean? Usually these quantum machine learning algorithms works in some hybrid mode, which means that some part of the computation is done on the quantum hardware and some part of the computation is done on the classical computer. Why? Because the quantum resources are much more limited and pricey and everything, and also due to these errors and so on. So usually, like especially in machine learning, it's the most common way is to split it and just like exploit the part of the algorithm in which the quantum computer can maybe bring some advantage, and for the rest use the classical one, the classical computer. And in quantum machine learning, there are two main groups of algorithms. One of them is called variational circuits, and the second one is kernel methods. I'm going to mainly focus on kernel methods, but I'm mentioning both of them. So just like quickly explain what variational circuits do. They are basically a group of algorithms which are like which works in some optimization loop, in which part of the optimization is done on the quantum computer. It's some parameterized quantum circuit. it does some stuff. At the end, we measure the state of the system, we get some output, we update some cast function, we process it on the classical computer, and based on that, we update the parameters of the circuit, we run this loop again, and we stop at some point when we are satisfied with our optimized result. So basically like some optimization, but with one quantum computing block in it. The more interesting part for me are kernel methods. I don't know if you're familiar with kernel methods from classical machine learning, but basically this stands on that with like extra quantum part to it. And that's what I focus on in my research. One of the, I guess, most popular algorithm from the group of kernel methods, the classical ones, is support vector machine. It's a classical machine learning algorithm, can be used for classification or regression. For purpose of this talk, we're going to talk mainly about the classification. And why it falls into the group of kernel methods is because it utilizes a thing which is called a kernel function. And what kernel function does in SVM is that it is some mathematical function which quantifies the similarity between samples, basically. You can have, it's a function, mathematical function, so you can have a more type. There are lots of types of these kernel functions, and based on the data set, based on the problem you have, you can choose the function which best fits your problem, or you can try multiple ones and see like what fits the best. But the point is that you somehow measure the similarity, and you can measure it in a different ways, in a different mathematical ways, therefore different kernels. So in SVM, you use this kernel to measure the similarity. You quantify it, and then you took it and put it into the model training, where what the SVM does, it takes the stuff from the kernel, which is like some matrix, kernel matrix, and then use these numbers in some optimization thingy. And that's the training part. The quantum part is, in this hybrid mode, is that you replace this kernel, this mathematical function, with a quantum kernel, which is basically like a quantum function, specifically like some quantum circuit. So you don't even have to look at it from a point of, this is a quantum part of the algorithm. You can look at it as just another type of kernel. And it works the same way. You pre-compute these similarities between the data samples. You just pre-compute them using quantum computer. You, at the end, get some matrix with all these numbers, which quantifies the similarities between all pairs of the data points in the data set. You take it and you put it into the classical training part of the algorithm, and then you train it and you look at the results. And in either case, you get more accurate, better performing model. Why bother with quantum SVM, or why am I talking about it? When I started working on this research topic, which is this quantum machine learning for malware detection, one of my motivations was the question what we can do on the quantum computing hardware we already have today. So not to wait for the super fault tolerant new universal quantum computer, but how to use this amazing, fascinating piece of technology we already have, even though it's not perfect. That's one thing. How we can use it for something useful in terms of like some real application. What does it mean, real application? I mean like application from a real world, not like some theoretical data set, some theoretical setup, but like something you could use for solving like some real problem. And the question is, could that be malware detection? That's the last missing buzzword in this long title. Why malware detection? Because I come from computer security background, and malware detection is a problem which is also solved through machine learning. And yeah, just originally came up with the idea could be the malware detection the use case. maybe first say what is actually malware detection. It's you can look at it as like some binary classification in the simplest case, which is just like saying is like some sample malicious or harmless. When you download a file from internet, what your antivirus software do is basically answering this question as well. And you can answer this question through multiple ways. In the simplest way, you can have a person who is like some malware analytic who look at the binary file and analyze it, and at the end came with the answer: is it malware? Yes or no. It is, or no, it isn't. In a more automatic way, you can check the signature of the malware file and see if it's already in some known database, and therefore you can say like, okay, it is malware. But because like you have lots of samples, it's like a classical big data problem when you have lots of samples and you want to somehow automate it, so you can solve it through machine learning. So maybe one more thing to add to malware detection. Maybe you can ask like, why bother with this super complicated quantum machine learning setup when we already have classical machine learning algorithms, models, which performs well? Like, why would someone should first invest their time and mainly resources to like explore this quantum machine learning area when we already have like well-performing machine learning algorithms? If you have a big data set, you can always beat it with some neural network and you're good to go. What is more interesting case when the data set gets smaller and smaller, then you're gonna use like some classical machine learning model, which is more suitable for the small data sets. So maybe SVM as one of the classifiers. And why am I talking about small data set? Because I'm kind of lying in this slide. The malware detection is like the easiest example. But for malware detection, we have a lot of samples. So we don't have to care about this at all. But when you want to do a thing which is like a subset of this problem called malware classification, which is, for example, classifying malware into different types of malware families, you are reduced a lot by the size of the data set. And you are then motivated to like use like some classifier which works well on the small data set problems. And one of them is SVM. And then like kind of connects with the quantum SVM. Can quantum SVM with quantum kernel maybe have better performance than the classical one? So that's just like some motivation to how it ties all together. How it works in practice. So what I actually do on those quantum computers. So I have some pipeline. First, I have those malware samples. I pre-process them. I'm not going to talk much in depth about malware files pre-processing, but I'm going to pre-process them. I end up with like some feature vector, which somehow describes the samples I have. I take these feature vectors, I encode them into quantum states, which coming back to the beginning are just like state of the quantum computer system. I encode them into the quantum computer. I compute the quantum kernel. I end up with some matrix with a bunch of numbers, which somehow describes the similarity between the data points. And I use classical SVM to train the model, and then I evaluate the performance. And in ideal case, I get whatever better performance. And what I do in practice is that basically evaluating this experimentally on the real data sets on real hardware. Because we have a bunch of theoretical research which supports the theoretical quantum advantage of this quantum machine learning approach, specifically these quantum kernel methods. But the question is, does it really work in practice on the hardware? And that's what I do. So I'm implementing it on the hardware, running the experiments on the hardware, and that itself is like a pretty hard task. Why? Because running experiments on quantum hardware comes with limits. And those limits are not just this not perfect quantum hardware, which is noisy and has errors and so on, but the limits are also more, how to say it, like software-wise or like pipeline-wise limits. I'm gonna mention the main three of them. So this may be a little bit more technical, but just like so you have an idea. The first limit when working with this quantum hardware is computational time. In real-world machine learning, we are used to having super powerful computation, super powerful machines. When you want to train some model, you don't even need like some fancy server. You can train it on your notebook. You may have depends on the model, depends on the size of the data, but like in some simple case, you can use your normal computer to train some model. Maybe you will have to run it for multiple days, depends on the use case as well, but it won't be pricey for you in terms of you're just gonna plug your computer into a charger. It will take some electricity, but it won't like cost you, I don't know, how much money just for using your notebook. With quantum hardware, because it's still in the research area, it is much more pricey to use this hardware because you are not the only one who wants to run experiments on it. And like just like having working quantum hardware is a very pricey thing because these quantum computers, the most most used ones from IBM, are based on like physical devices or like no technology which needs a lot of cooling, which takes a lot of energy and everything. So it's just in general just pricey. You're not the only person who wants to use it, so it's gonna cost money. So your computational time is limited. So analogy to real life. Imagine you would want to train your machine learning model on some fancy IoT electronic toothbrush. It would probably be somehow possible, but you would have to do a lot of optimization. It would take you forever. And maybe you would be, if you would be very motivated, let's say that someone told you that if you're gonna use this specific IoT fancy electronic toothbrush, you will get like super good results. Then you would be really motivated to optimize your algorithm and train your model for months just to get some results from this toothbrush. So I would say like this is nice analogy. We don't train our normal machine learning models on toothbrush, but let's say this is a fancy toothbrush. So that's one of the limitations. So what it means in practice, you have to do a lot of optimization from the software part just to make it run, and then it runs forever. You have to wait in some quiz. You are very restricted of the computational jobs, everything. That's one thing. The second thing is you have some, when you're writing normal code in like some normal programming language, you don't write it in like those hardware instructions. You don't write it in assembly. You would, if you come from maybe, for example, from CTU, you would maybe use some low-level language like C or C++, but who, I don't know, does anyone here program regularly in C or C++? Okay, one person. Okay, 3 people from this whole room. Still C or C++ are still like not the most low-level programming languages, and most of us don't even work with them. You would use, I don't know, Python, or like if you do machine learning, probably Python. If you do, I don't know, whatever else software engineering job, you would use something else, but it will be like some high-level programming language. And then what happens when you use this high-level programming language? You sometimes, you somehow have to compile your code to actually run it on the machine. You don't do it, the compiler does it for you. If it's Python, it's like, how to say it in English, like in the process. If it's C++, you compile it and you run it. But the thing is, you don't do the compilation yourself. You just like write it and in some your language which is understandable to you, and that's it. Imagine you would have to write your code in assembly. It would also take you a lot more time. And then even in the assembly, you would still have to then compile it to the specific instructions for the hardware you're using. And this is basically what transpilation is, like analogy to it. You have some quantum algorithm, which consists of like some operations with these quantum gates, which somehow changes the states of your system. And you are using like your ideal set of gates of these logical operations. But then you want to run it on a hardware, and the hardware doesn't support all these gates you want to use. So what you have to do, you have to transpile your circuit, which means like translate it to the gates which are on your dedicated hardware. And what this process does is it will make your circuit usually much more deep, or in normal language, complicated. It will introduce additional gates, and it will most likely degrade the performance, because adding more gates will make your algorithm more noisy, more susceptible to these errors. And then you might end up with algorithm or with code which gives you at the end like some random result. So the transpilation itself for the hardware is like a big constraint in the process, because you may have a nicely working quantum algorithm, but then you transpile it and you lose all these advantages. So you also have to optimize this process based on the hardware you're working with. And the third constraint is software. So for these devices I'm working with, which are from IBM, there is the software tool SDK. It's called Qiskit, and it's like the most popular SDK for working with quantum computers. The problem is it's not a production-ready SDK. What does it mean? It changes constantly in terms of like major changes. Imagining you are using whatever library you are using, I don't know, in machine learning, scikit. So imagine that every few months, scikit drastically changes in terms of you have to rewrite most of your code, because like the methods which were supported 3 months ago are no longer supported. Something like this is Qiskit. So it's pain in the ass, extra pain in the ass to all of this process. I'm a biggest fan and also biggest hater of Qiskit. Biggest fan because it's like the best software we have for working with quantum computers. It's really good. And biggest hater because it's also not the production-ready software I'm used to working with in normal software engineering. And another thing is it's mainly suited for work with quantum simulators, which are as it says, simulators of quantum devices. It's not real hardware. It's a piece of code which simulates the quantum computations for you locally on your computer. And it's just like I don't know, like a thing you use before you run the software on real hardware to get at least some expectation of what your code is doing. But to run the code on real devices using Qiskit, you usually have to do it yourself. And that's another thing. So these are just like three like main technical constraints, I would say, which are extra painful when you want to do anything on the real hardware, on the real quantum hardware. Where are we now? Or where I am with my research. So it runs on hardware somehow. But what this somehow means, it still does not have much meaning for the practical use. So where I show all these, when I started talking about what I do for my research and the questions, I still don't have answer to them. If I would have answer to them, I would probably not be talking about it here, but maybe in like some, I don't know, to some investors to sell my amazing quantum solution. I'm a researcher. I'm not trying to sell you my product. So to be honest, I still don't have answer to these questions. I'm much more far away than when I was 2 years ago when I started working on it. But the current state is that and it's not just malware detection, just in general with quantum machine learning, we have a lot of theoretical research, a lot of research which experimentally supports the results either numerically on the simulators, but not on the real hardware. And the question is how it's gonna perform on the hardware, because that's what it's about at the end. And on hardware, we are limited due to all these things I told before. So by a small number of training samples, I mean like really, really small number of training samples in terms of like you can get any like reliable results from them in terms of like machine learning, like tends to like I don't know, few hundreds of samples at max. That's the more ideal case, and that's like nothing when you would want to compare. It's nice for the proof of concept, but it's like nothing when you would want to beat a classical well-performing optimized classifier for a small data set. So that's the state right now. Yeah, so not much meaning for the practical use yet. And yeah, I already did some experiments and have a publication about it. So yeah, I have some results, but not something fancy I would present here. And that's it. Like that's it. You maybe this is the point when I can tell you sell you my product or tell you to invest in quantum computers, but I don't have any like nice punchline at the end. Like that's it. That's the state. That's the work of a researcher. Yeah, I don't have the answers, and yeah, I don't have them for now. Maybe in a few years I will be here talking about this, how I found the quantum advantage and have the real application, but not have it yet. And yeah, that's it. Thank you for your attention.
I will just briefly mention that we will post the slides both under the YouTube recording and on the meetup page. So if you didn't catch, I know you tried to catch one reference, right? You will have a chance. And now there's space for questions for Eliška. If you have a question and you're online, just type it into chat and I will ask it for you. If you're in the room, I will hand you the mic. Right?
Thank you for a nice talk. I was curious about kernels that we're mentioning, because the standard kernels have names I found familiar, but the quantum ones had fancy names. Do they also have fancy properties that you are hoping to exploit?
Yes.
Are they mathematically surprising?
Yes. Like the kernels which like should have theoretically have some quantum advantage are briefly to say like are kernels which are believed to be hard to classically simulate. So when I was talking about these simulators, they are just simulators, and when in general when you have a quantum computer simulator, it's just a simulator, so it can simulate certain stuff pretty good. But when there is, for example, a property called entanglement, which I didn't want to go too much into the physics behind it, but certain things, certain circuits are very hard to simulate. And these kernels, these quantum kernels I mentioned there, are exploiting these properties. So for example, very entangled circuits with like specific operations, specific gates, and which are believed to be hard to simulate, and also good for this type of problem.
Yes, thank you. Any other questions? Give me a sec, sorry, so that people online can hear you. Yeah.
So why does it become harder to simulate, specifically when you have to deal with entanglement, and easier when you don't?
Entanglement is like some physical property which is specific for quantum physics, quantum mechanics, and simulate entangled circuits is just like much harder because it's not a property in classical physics and classical mechanics, and classical computers work on classical mechanics. So to simulate it, you like can do it to a certain point, like classically, but like it's like a property which happens in like those small quantum particles. So it's hard to do it with like devices which like don't have it. That's like a very brief answer. To explain what is entanglement, I'm gonna try to give. Do you know? I don't know. Do you know what entanglement is? Okay. The two others, so it's this special property. When you have entangled qubits, these entangled units of information, when you take two qubits which are entangled and you take just one of them and you want to read the information in them, you cannot read it. You won't like get any information from one of the qubits themselves, just by itself. If you want to get any information from these two qubits, you would which are entangled, you would have to read them both simultaneously. I heard a nice analogy to it. Imagine you would read a quantum book which is entangled. If you want to read a quantum book, you would have to look at all the pages simultaneously at once to get the information from the book. If you would read just one page from the book, you would get nothing, like nothing, no information about the story which is in the book. If you want to read the story, you would have to look at all the pages on the ground. You would have to look at it all together, read it all together, and then you would get the information. So that's kind of analogy to what entanglement is. And this is something which is hard to simulate classically. You can simulate it to some extent, but it will take you much more time with the classical computers, much more resources, and you can simulate it effectively to a certain amount of qubits, but more qubits you have, the harder it gets.
Nice. So we have two questions online. The first one, I'm going to try to summarize it, is I believe that Google recently announced a 2-qubit gate that has above 99.99% fidelity.
Mm-hmm.
And the question is, would that influence your work if you had access to this hardware?
I can have the classical answer, I don't know, yes or no. I would have to see. I don't think so. I don't think so because the main point or the main challenges I'm facing with, it's like not that much about the technology or about the quantum computers themselves, but all the extra software or classical pipeline stuff which are related to it. Then if someone would build it for me, if all of these constraints wouldn't happening, then what I would do, I would experimentally compare the results with these gates and the other gates, and I would see what the outcome is.
Nice. Thank you. And one more. There's a question about the data set. Is it small because you don't have access to more malware data, or because it would be too much strain or slow for a quantum computer?
Again, yes or no. In general, when not talking about malware detection, but in general with the quantum machine learning, when you're looking for an advantage and not just the advantage like quantum advantage, you are also looking for advantage on a use case on which makes sense. So it doesn't make sense to try to apply quantum machine learning to something where we can solve it very well with classical machine learning. So when you have a large data set on which you have already very well performing classical models, why to bother with quantum machine learning? The better use case is to look at problems which have small data sets by nature of the problems, in terms of they are, I don't know, hard to call it. It doesn't have to be malware detection at all. It can be, I don't know, medical data. You have some data from just a limited amount of patients, and on these data you want to train the best classifier, but you are limited by the amount of data. You will, even in classical machine learning, you will look for the best performing classifier on this small amount of data. And the quantum part is just extra thing to it, because in this use case it makes sense to try to look for the quantum advantage. It doesn't make sense on large data sets.
Nice. I think I understand. Right. Are there any other questions? All right. So with that, let's thank Eliška for the amazing talk again.